All right, in this video, I want to prove some of our circle theorems with respect to inscribed angles. And our first theorem is inscribed angle theorem. That tells us if an angle is inscribed in a circle, then its measure is equal to 1/2 the measure of the arc it intercepts. In other words, if we know the measure of arc AD here, we know the measure of this inscribed angle ABD will be half of that measure. Now, how do we know this is true? How do I know that my math teacher isn't just telling me this? Trust me, take my word for it. Let's go ahead and prove it. And when we prove it, we'll be confident that it's true and we'll be more likely to remember it. And if we forget it, we'll be more likely to be able to rederive it. What we're going to do here is we're going to make sure that we can prove all three of these conditions are true for all inscribed angles. We've got three possible conditions to look at. Condition 1, we've got an inscribed angle where one of the sides of the angle is coincident with a diameter in the circle. Condition 2 is where the inscribed angle straddles the center of the circle, like this. And condition 3 is where the inscribed angle lies entirely on one side of the center of the circle. I'm going to prove all three of these conditions. Let's start with condition 1. All right, let's take a look at condition 1. Given here that angle ABD is inscribed in circle C, could we prove that the measure of angle ABD is half the measure of this arc AD that it intercepts? Okay, let's tackle this. Let's go ahead with a two-column proof, and we're going to restate the given information. We've got angle ABD is inscribed in circle C. That's our given. Where do we want to go from here? Well, the first thing I want to do is I'm going to go ahead and draw just an auxiliary line. Okay? There's no reason you can't, at any time you want in geometry, draw a line between 2 points, because 2 points define a line. So I'm going to draw that auxiliary line right there from C to D. I'm just going to say I'm going to draw auxiliary line CD, and the reason I can do that is because 2 points define a line, right? All right. What do we do next? What's the significance of that line? Well, hopefully you recognize that CD, or any line that you draw from the center to the edge of the circle, is a radius. And since CD is a radius and CB is also a radius, I'm going to mark those congruent. I'm going to go ahead and state that CB equals CD. And the reason is all radii are congruent in the same circle, right? Okay. All right, so anybody see anything interesting about triangle BCD? Triangle BCD looks like an isosceles triangle to me. So I'm going to go ahead and say that the measure of angle B is congruent. Or I should say the measure of angle B. I'm going to work in equality here rather than congruence. The measure of angle B equals the measure of angle D. And the reason is that base angles in isosceles triangles have equal measure. Excellent. Okay, so if they have equal measure, I'm going to go ahead and mark them congruent. I am skipping the step of declaring them congruent using the definition of congruence and all that. Where would we go next? If we want to prove that the measure of this angle is half the measure of this arc, well, is there some way I could relate this angle B, to this arc? I'll give you a little hint. I think that the measure of angle B plus the measure of angle D should add up to what? It's going to add up to the measure of angle ACD. How do I know that? How do I know that these two angles add up to this angle here? Well, angle ACD is an exterior angle. in this triangle. So this is exterior angle theorem. Hopefully you remember that from chapter 5 when we did that unit on relationships and triangles. So I know these two angles add up to equal this one. Now the significance of that is that angle ACD is a central angle that intercepts this arc that we're interested in. So could I say that the measure of angle ACD equals the measure of arc AD, this arc? And the reason is, well, that's our central angle theorem, right? Or you could say central angles have the same measure as the arcs they intercept. Okay, good. I'm going to go ahead and rewrite this statement here that I made. Measure of angle B plus the measure of angle D equals the measure of this angle ACD. Why am I doing that? Let's see where that goes. I'm going to rewrite this as the measure of angle B plus the measure of angle B equals the measure of angle ACD. What did I do there to get from this step to this step? Hopefully you notice that since the measure of angle B equals the measure of angle D, what I did there was a substitution. I just substituted in the measure of angle B for the measure of angle D here, so I could rewrite that. And I could further simplify this and write it as 2 times the measure of angle B equals the measure of angle ACD. And that's a substitution as well, isn't it? Recognizing that 2 times the measure of angle B is the same thing as the measure of angle B plus the measure of angle B. Now, every now and then I've told you guys it's good to look back at your dashboard, your GPS, and see where you're headed. Notice we are looking eventually for something that equals 1/2 the measure of angle of arc AD, right? So I'm tempted to divide both sides of this by 2 and say that the measure of angle B equals 1/2 the measure of angle ACD. And what did I do there? I just did the division property of equality, right? Okay. Anybody see where we're going from here? I've got the measure of angle ACD equals the measure of arc AD, right? Central angle theorem told us that. So I should be able to say the measure of angle B equals 1/2 the measure of arc AD, right? What I'm going to do is just substitute. Since the measure of angle ACD equals the measure of arc AD, I'll substitute the measure of arc AD in for the measure of angle ACD there so that I can rewrite that equation. All I did there was substitution. And the measure of angle B here really is the measure of angle ABD equals 1/2 the measure of arc AD. They are in fact the same angle, angle B and angle ABD. So did we prove what we were asked to prove? Does this match our dashboard? Indeed it does. So we've done a substitution here and our proof is done, QED. All right, now that we've proven that condition 1, we can use it to prove conditions 2 and 3. Here's what that's going to look like. If we're looking at condition 2 here, given that we have angle ABD inscribed in circle C, let's go ahead and just state that. That's our given information. Angle ABD is inscribed in circle C. That's our given. Okay, how are we now going to prove that this is true in this condition as well as the first condition? Well, what I'm going to do this time is draw an auxiliary line, but I'm going to draw it a little bit differently. I'm going to draw an auxiliary line from B to C and extend it to point E that I'm going to call on the edge of the circle. And basically what I mean by that is I'm going to draw this auxiliary line here. Okay, I'll draw it as a dashed line. I'm going to extend it to point E. We're just going to call that point E, where that lines go on infinitely in both directions, and where it intersects the other side of the circle is point E. And the significance of that, as you probably recognize, is that BE is a diameter, which makes it kind of similar to that condition one that we've already proven. So drawing the auxiliary line, our reason there, 2 points define a line. Okay, and where do we want to go with this now? Okay, so I'm looking at the measure of angle ABE. This is a condition that we already proved. So I'm comfortable saying now that the measure of angle ABE equals 1/2 the measure of arc AE, this arc that it intercepts. This inscribed angle equals 1/2 the measure of this arc. And the reason is, I'm going to just call that inscribed angle condition 1, because we've already proven it. Once you've proven something, it goes in your bag of tricks, and you own it, and you can use it any other time you want. All right, good. I think I see the same condition here with angle EBD. That is an inscribed angle as well, so I could say the measure of angle EBD equals 1/2 the measure of the arc that it intercepts, which is arc ED. Good. Okay, inscribed angle condition 1, same reason. Good. Okay, where are we going to go with that? Well, I'm looking at the fact that angle ABE plus angle EBD adds up to this inscribed angle ABD, which is the one we're looking to prove, right? So I'm going to go ahead and state that the measure of angle ABE, this guy, plus the measure of angle EBD equals the measure of angle ABD. How do I know that? That is our angle addition postulate. In the past, we've abbreviated that as AAP, but that's going to be ambiguous now because of the next step we're going to do here. Hopefully you recognize what that is. Where are we going? And I know these arcs here are relevant. And together I could say that the measure of arc AE plus the measure of arc ED, these two arcs add up to this longer arc AD, right? So the measure of arc AE plus the measure of arc ED equals the measure of arc AD all the way through. And that is arc addition postulate. That's the ambiguity I was talking about. We can't use AAP anymore. That would be ambiguous. Okay, so looks like it's all coming together here. And maybe we can take this measure of arc AE plus the measure of arc ED equal to the measure of arc AD, and maybe we can do something with that. What could we do with that? We have this measure of angle ABE plus the measure of angle EBD. We could substitute these in here, right? We could get 1/2 the measure of arc AE plus 1/2 the measure of arc ED equals the measure of angle ABD. What we did there was we substituted these into this equation here. So that was just a substitution. Okay, so we've got that. That looks good. I'm tempted to factor something out of this, particularly on the left side. I'd like to factor out the 1/2. I'm going to factor 1/2 out of each of these terms, and I'm left with 1/2 times the measure of arc AE plus the measure of arc ED equals the measure of angle ABD. And, oops, I forgot my parentheses there. What I did there was reverse distribution, right? Or you could say distributive property. Okay, we just kind of undistributed the 1/2 out of those. Okay, that's significant because look at what we can substitute in now, because we know that the measure of arc AE plus the measure of arc ED equals what? We can substitute that in here. And we get 1/2 times the measure of arc AD equals the measure of angle ABD. Is that what we were being asked to prove? Yep, if you want to flip it around with the symmetric property, you can. What we did here was a substitution. And you can always take one more step and flip it with the symmetric property, but I think you can see that we have pretty much proven what we were being asked to prove. QED. So we use that condition 1. That was good that we started with the condition where one side of the angle was lying on the diameter, because now we can use that to prove when it's straddling the center of the circle. Condition 2. Let's see if we can do the same thing for condition 3 when the angle lies entirely on one side of the center. All right, let's go ahead and see if we can prove condition 3 in a similar way that we proved condition 2. You can see I've restated the given information. If you guessed correctly, probably thought that I would draw another auxiliary line. We'll draw auxiliary line BC and extend it to point E on the edge of the circle, because 2 points define a line. Good, so that's going to look something like this. We're going to draw a little dashed line going from B through the center point C until we hit the other side of the circle, and we'll mark that point E. Good. And where are we going to take our proof from there? Well, you might recognize that this inscribed angle EBD looks a lot like that thing that we proved in condition 1. So let's go ahead and state that we know the measure of angle EBD is going to equal 1/2 the measure of this arc EAD. Okay, and that is our inscribed angle condition 1 that we've already proven. Once you've proven it, you own it, you get to use it again. Good. Similarly, you can see that we've got this angle EBA that meets the same criteria as condition 1, where one side is coincident with the diameter. So I could say that the measure of angle EBA equals 1/2 the measure of this arc EA that it intercepts. Good. Inscribed angle condition 1 again. Okay. All right, and I'd like to say that I can use arc addition postulate to, instead of adding these together, I could say that I know that the measure of this angle ABD is going to equal the measure of this angle EBD minus the measure of this angle EBA. It's just a rearrangement of our angle addition postulate, right? I can, if I know these two angles add up to this larger angle, I can subtract this angle out of the larger angle to get this guy. So that's our angle addition postulate. Good. And likewise, we can use our arc addition postulate in the same way. We could say that the measure of this arc AD, which is one of the things that we're after, the measure of arc AD is going to equal the measure of this longer arc EAD minus the measure of this smaller arc EA. Good, and that's our, instead of angle, that's our arc addition postulate. Okay, good. Where are we going to go from there? All right, from there I could say that the measure of angle ABD, I think I can use a substitution here. The measure of angle ABD is going to equal, since I know the measure of angle EBD equals half the measure of arc EAD, I can substitute it in there. And I know the measure of angle EBA equals half the measure of angle arc EA, so I can substitute that expression in there. And I'm going to get the measure of angle ABD equals 1/2 the measure of arc EAD minus 1/2 the measure of arc EA. Good. And what did I do there? Well, I just substituted in those equivalent expressions. Good. I think maybe I can factor something out here. I could rewrite this and say the measure of angle ABD equals, let's factor a 1/2 out of each of these terms, and we'll have left over the measure of arc EAD minus the measure of arc EA. Okay, what did we do there? That's the distributive property when you factor something out. That's all you're doing is using the distributive property. Good. And now that I've got this measure of angle EAD minus the measure of angle EA, that looks suspiciously familiar. That looks like this guy right here. So I can go ahead and substitute that in. And I'll get the measure of angle ABD equals 1/2 times, I'm going to substitute in the measure of arc AD right there. How do I justify that? That substitution, take a quick glance up at your dashboard. Does this match what we were being asked to prove? In fact, it does. QED, all set. All right, the last theorem with respect to inscribed angles that I want to prove here is our circle theorem 9, which states that if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. In other words, angle M and angle O will be supplementary. They'll add up to 180 degrees. And angle L and angle N will also be supplementary. Okay, how do we know this is true? Let's go ahead and prove it. So we've got our quadrilateral LMNO. Let's just go ahead and restate our given information. Quadrilateral LMNO is inscribed in circle C. Good. And that is our given information. Okay, where do we want to go from here? Now, based on the theorems that we've already proven, I can see that this angle LMN is an inscribed angle in this circle, so I know the measure of angle LMN is going to equal 1/2 of the measure of the arc it intercepts. Let's call that arc LON. I'll go ahead and highlight that because that'll actually help visualize what we're proving here. Okay, that arc, angle LMN, intercepts that arc. So it equals 1/2 the measure of this arc LON. Good. And that is our inscribed angle theorem, right? That we've already proven. Once you've proven it, inscribed angle theorem, excuse me. And we proved all three conditions, so we know this is actually condition 2. But since we've proven them all, we've got one unified theorem. We'll just call it inscribed angle theorem. Likewise, I could say that the measure of this angle LON, the other one involved in what we're trying to prove here, is going to equal 1/2 times the measure of the arc that it intercepts. And it looks like it intercepts arc LMN. Arc LMN. Okay, that's inscribed angle theorem as well. And you'll notice that when I highlight this other arc, something should jump out at you. Excuse me, I'm going to just highlight this guy here. Something should jump out at you. Hopefully you notice that we have this minor arc and major arc that add up to the entire circle. So maybe we could state that. We could state that the measure of arc LON plus the measure of arc LMN equals 360 degrees. And that is definition of, I'd say a definition of a circle, but you might also say minor and major arcs. So what do we do with that? We want to know that the measure of angle LMN plus the measure of angle LON equals 180. So let's go ahead and add these together and see what we get. If we added the measure of angle LMN plus the measure of angle LON, we would get 1/2 times the measure of arc LON plus 1/2 times the measure of arc LMN. Good. All we did there was addition. We just added two equations together. Okay. Now I could factor out that 1/2 like we did in our other proofs. I could say the measure of angle LMN plus the measure of angle LON equals, let's factor out this 1/2, and what do we have left over when we're done? The measure of arc LON plus the measure of arc LMN. Good. What we did there, we factored out a 1/2. We just used the distributive property. Or you might say we used it in reverse, but that's what factoring is. Good. Now, look at this. That looks suspicious. The measure of arc LON plus the measure of arc LMN we figured was equal to what? Those two arcs together add up to 360, a full circle. So can we go ahead and substitute that in there? And get the measure of arc LMN plus the measure of, the measure of angle LMN plus the measure of angle LON equals 1/2 times 360 degrees. Hopefully you see where we're going with this. We just did a substitution there, right? And we can substitute again and say that the measure of angle LMN plus the measure of angle LON equals 1/2 times 360 is 180 degrees. So I'll just substitute that in. Is that what we were asked to prove? Indeed it is. So we can say QED, quod erat demonstratum, that which was to be demonstrated. Good. I hope you guys found these proofs helpful. Proving these theorems really helps you understand them on a much deeper level. Hopefully it helps you remember the theorems better, and like I've said before, it should help you be able to rederive them if you ever forget them. Thanks for watching.